Good morning, developers. If you are new to the channel, my name is Robin. It is Algorithm Monday, the day that we take batting practice, or we do layups so that we are ready when game time comes. And today we're going to look at insertion sort. We recently did bubble sort, and I decided to parlay that into a playlist on sorting algorithms. So I'll drop both of those links into the description, so check them out if you want to. Insertion sort is the next obvious step, I think, to bubble sort. Bubble sort is sort of the entry point for talking about sorting algorithms, maybe even algorithms. Insertion sort is a great next step because it is almost just as simple. It is easy to implement, but it is better in an adaptive way. And we will talk about that in a minute here. Something to know up front is the best case for this algorithm is a big O of n, and the worst case is going to be n squared. So this is not an appropriate algorithm to implement. You can do much better. This wouldn't be acceptable in modern terms, but if the list is in perfect order, it's going to have a big O of n. If it's perfectly out of order, we're going to have to do n squared. So you'll see that here in just a minute. The way that it works is that we will have an outer loop. So that's going to be the end part. We have to loop over every single place, just like bubble sort. The different part here is we are going to start from the left. You could start from the right. I don't think it would make any difference. You would just do things in reverse. But we're going to call this the key. I think that's a better term than the pivot. That's what we use in heap and merge, which is really confusing. This is still pretty simple. But we have our key. And so we have an I of 0 on the outside, which means our key will be the number 1. And what we do is we compare that to everything to the left. And if this is bigger, then we leave it where it is. If it's smaller, we work our way to the left, which again you will see. Just like bubble sort, we don't have to do the very last one because there's nothing to compare it to. Same thing here. This is the first one, so we don't have to do anything. We go on to where I equals 1, and that means our key is going to be the number 3. It is the thing in the slot or index 1. Is that smaller than the number 1? It's not, so we don't need to do anything. We are done. We go on to the next one where I equals 2. That makes our key the number 4. Is that smaller than the number 3, the one that precedes it? It's not, so we move on. We go to I equals 3. That makes our key the number 5. Is that smaller than number 4? It's not, okay? So you can already see, I hope, the advantage over bubble sort. We don't know that these are in the right place, okay? In fact, 3, 4, and 5 are all not in the right place. They're going to need to get shifted in a second with our 2. But because they are in order relative to each other already, we don't have to do any more operations. If 5 is in the right place against 4, we know it's in the right place against 3 and 1 because we checked against 4, we checked against 3. So they're all in the right place as we move along relative to one another. So we get to the next one and we finally have something to do here. When I is 4, the key is the number 2. Okay? So we check to see, is this bigger than the previous number? It is not, which means they need to switch places. But instead of switching them, when we implement this, we are going to simply get rid of that, and we're going to put 5 here. Now that's okay because we're going to store our key. We know that 2 is the number that we are looking for. We go to the next spot. Okay, so this one, 4. We check 2 against 4. Is 2 bigger? It's not. So we overwrite this spot with the number 4. 4 needs to move up relative to our 2. So our 2 is working its way back. We check 2 against the number 3. Is it bigger? It's still not. So we get rid of this and we put the number 3 in there. We're finally back to this spot here. Is 2 bigger than the number 1? It is, which means this is the place where we insert our key. That's why it is called insertion sort, because we're looking to insert it in the correct spot, again, relative to all of the places that we have checked. So we now are at 1, 2, 3, 4, and 5. Those are all in the right position. For the last one here, we will do I equals 5. That gives us a key of 6. Is 6 bigger than 5? It is, so we don't need to do anything. The list is sorted. That means that we had an almost insorted list, but instead of n squared, the first time through, we didn't do anything. The second time, or the second index, I guess, we had to just check 1. Done. Here we had to check 1. Done. Check 1. Done. Check 1 2, 3. We had to go all the way back. And for this last one, we only had to check 1 and we were done. So this is almost n. It would be almost worst case with bubble sort because of this 2. This 2 is in a spot that's causing us to have to check every single number every single time through. Remember, bubble sort is bubbling up, so we can guarantee after the first iteration that the biggest number is in the right spot. We can't guarantee the list is sorted until we get to the end with insertion sort, but we can save ourselves a lot of operations if the list is mostly in order. Okay, that is how insertion sort works. Let's go code it out in Python. I am over to VS Code. Of course, use any code editor you want, but insertion sort.py, and I've got a little bit of code here to walk through. If you're not familiar with Python, you should still be able to follow along and try and implement it in whatever language. I have bubble sort open in case we need it. I don't think we will, but we've got the time module so that on line 3 and line 13 we can grab the start and end time. Line 14 print off what the difference is. Line 2 I brought in the random module. On line 9 here, I'm using list comprehension. We'll do this at the very end, but we can grab a random integer between 1 and 1 million and then generate a list of 10,000 of those numbers, and we'll convert that, or we'll use that for our array. Line 5, we've defined a function as insertion sort that brings in on an array. Pass is only there because when I was setting this up, this red line was there. Python or Visual Studio Code, I guess, doesn't like nothing in the function, so that's not going to be there very long. This is what we had on the board: 1, 3, 4, 5, 2, and 6. We call insertion sort and pass it the array, and then we print off our sorted array. Okay, let's implement insertion sort. We're going to start off with a for loop for I in range from 1 out to the length of the array. So we can make a note here quick. We start the outer loop, and I'll put a note here. That is the position we are on at 1, not 0. We don't search that first or the 0 index because it's already in the correct position relative to itself. So we start at 1 and we stop when we hit that hit the length of the array. We're going to define our key, and that's going to be at array I. This is the thing we want to put in. Let's do insert into its right spot, and I'll put in parentheses there, relative to the left. So this thing we are after, each time through the loop, it will be in the right spot for everything at I and before I. We will define j, and j is going to be I minus 1. So we looked at this on the board, but j will start at I minus 1, but we will decrement it. Each time through our while loop, which we are about to define, we are going to drop j so that we can keep checking the numbers to the left of I. Okay? We'll have our while loop that needs to be inside of our for loop. While j is greater than or equal to 0. You can do greater than -1. Of course, that's the same thing. The reason that this needs to stop when we get below 0 is because that means we have run out of numbers. When we get to the 2, we're going to check this j, and then this one, this one, this one. If we get past that, then we have to stop. Our second condition is going to be while array j is greater than our key. We are comparing the key to the thing that is at array j, and if it is bigger, then we need to overwrite what is at j plus 1 with whatever is currently at array j. If this doesn't make sense, I'll show you an example here in just a second. Okay, so array j plus 1 is going to equal whatever is at array j, not the key. We don't do that until the very end. We're going to decrement j by 1. Outside of our while loop, we'll do array j plus 1 and set that equal to the key. This is our whole implementation. Let me walk you through it. The first time through the loop, so our for loop, I is going to equal 1 because we start at 1. J is I minus 1, which means j is going to be 0, and our key is going to be whatever is at array 1, which is the number 3, so our key is the number 3. So we go to our while loop. While j is greater than or equal to 0, is it? It is. It's the number 0. And array j, so what is at array 0? The number 1, so we've got a 1 here, Is that bigger than our key, which is the number 3? It's not. So we don't ever run this even one time. So let me switch that back over. We overwrite what is at array j plus 1, which is I, to the key. We insert it, and I'll go ahead and make that note. Insert our key. We're doing a little bit extra work, and we can come back and look at that because that's not necessary if we don't make any change, but that is the first time through. So we still have the exact same list after one iteration. The second time through, I'm going to copy this because it's pretty much going to be the same thing. We bump I up to 2. So in our for loop, our j is now 1 less than I, and our key is the next position, which is 4. The exact same thing happens. J is greater than or equal to 0, but array j is the number 3. 3 is not bigger than 4, so we don't do anything. We still have the same list. We'll go to the next one. I is 3, j is going to be 2, the key is 5. You already know, nothing happens. So let's copy this, and then we get to do something interesting here. When I is 4, j is 3, our key is going to be 2. So we get up here, this is true. What is array j? Well, it's 5. What is our key? It's 2. Finally, we have something to do. So we're going to go to j plus 1. What is j plus 1? It is this spot. It is at I right now. It's not always going to be, but we're going to go to that spot, and we're going to overwrite it with what is currently at j. So let me undo that. Come down here, grab this, and I'm going to move over 1. So we go to j plus 1. That's this. This is j. This is I. This is j plus 1. We're going to grab what's at j, and we're going to overwrite it like that. So that's what our list looks like after the first time through. I'm going to copy this because we decrement j, so j drops down to 2. Back up here. Are we still greater than or equal to 0? We are. We're at 2. Is what's at array 2 bigger than our key? Well, what's at array 2 is the number 4. It's this 4, I guess. Is 4 bigger than 2? Well, yes, it is. So we do the same thing. We grab our list. I'm going to bump it over again. We go to j plus 1, which is this, and overwrite it with j. So we just shifted the 4. Copy this whole thing. We decrement j, so j is now 1. We bump that over one more time. The whole process is the same. We're going to grab 3 and overwrite the 4 because it is still bigger. Paste this in one last time. I is still 4. J is now down to 0, and the key is still 2. Is 1 bigger than 2? It's not. So we insert our key into that position, and this one is done. Come back up, copy this one last time for our last iteration where I is the number 5, j is going to be 4, the key is going to be 6. We don't do anything, the list is in order, and we are all finished. If we come over and we run our code, we have a happily sorted list that took 0 seconds to solve. Let me comment out our array there and bring in line 34. This is going to be a little bit ridiculous on the screen, but hopefully, yeah, there we go. So it only took 1.1 second to do 10,000 numbers. And as you can see, I'm not going to scroll up because it's hard on my eyes, but it is in perfect order. Just to prove it to you, I guess I will print off the array before, I guess instead of the final. So there's our good and mixed up array. Takes about the same time. Okay, things to remember here. I'm going to bring this one back in. Actually, let's leave it that way. That's how you will get it in the repo. Things to remember. This is a big win over bubble sort because it is adaptive. We didn't have to do anything here because our key is smaller than the next number, so we don't waste any operations. Our key is still smaller, so we don't waste any operations. Same when we get to the point where we actually have to do some shifting, we shift each number ahead. So we take the 5 and move it there. We take the 4 and move it there. The 3 and move it there. Finally, we insert the key into its correct position for everything at index 4 and before, which are all of these numbers. So a big improvement over bubble sort if the list is close to sorted. If it's just a totally random list, it'll just depend on how lucky you get, whether it's better. The best algorithms are still ahead of us, so please tune in for another Algorithm Monday. I will see you next time.